particle physics theoretician with a long way in producing ideas for physics. He has been everywhere till he landed at CERN in the late 70s at the theory division to eventually become the division leader. CERN is, as you know, an experimental laboratory, so what are these guys doing there? Well, they are responsible for producing ideas, because the experimentalists only produce data. And they will never know what to do with data, petabytes of data, mountains of data, without the illuminating minds of the theorists. The Hochula is interested in everything that is intriguing, that is puzzling, that is catastrophic in the universe, going much beyond of standard physics we experimentalists do. I hope that in his next talk he will enlighten our dark minds about everything we still don't know about the universe, because it is his job to produce ideas as crazy as possible to become true.
Thank you very much, and thank you for the invitation. May I have my screen, please? Well, since I don't have my screen, I will explain that my name is not Alfredo, but Alvaro. However, since I'm a kind man, I'm going to give the talk anyway, if they allow me. Okay. I'm not an experimentalist, but I always start with a test, just in case. And I wasn't able to transmit the title of my talk to the organization. The title is The Photon, which will be labeled Gamma, and its siblings. And the first question about light that was scientifically very important was whether it was an ensemble of particles or it was a wave. And that, the answer is peculiar. It's both things. And as the vice president of the Academy already mentioned, this was first understood by Einstein. He mentioned it, but he didn't quite explain it completely. Einstein wrote this formula, for which he got the Nobel Prize, not for the other one that everybody knows. And the formula says that a wave of light of frequency nu is a particle or an ensemble of particles of energy E, up to a conversion factor, which is just a constant. So that means that frequency and energy are the same thing, only in different units. It's like money can be put in units of dollars or put in units of euros. The constant changes with time. It's not a constant, but it's the same thing. It's money. Now, perhaps the most fascinating experiment about light is the following. You take a source of light and shine it into a screen, onto a screen that has two slits. And if the frequency, if the wavelength of the light is much smaller than the opening of the slits, then you find an image here in blue of the slits, one or the other slit. However, if you increase the wavelength to become comparable to the size of the holes, then instead of two spots, you find an interference pattern, such as the red one in here. I'm going too fast. An interference pattern as if the two slits acted, each one of them, as a source of new waves, like waves in water, that would interfere and produce a pattern of arrival to this detector that tells you, counting how much energy is deposited in every black slit. It shows an interference pattern. Now, that is if you shine photons from the light source. But imagine that you have the same light source and you shine the photons one by one. Then something very interesting happens, which is sometimes a photon hits there, and other times it hits there, or it hits there. But if you want to wait long enough and count the number of times that the photons have hit the detector, it turns out that the pattern of the arrivals is again a interference pattern such as this. That means something very peculiar, and that is that every photon went through the two slits. Every single one photon went simultaneously through the two slits. That seems to be a very surprising fact, but sorry, this is the way that the universe in which you happen to live works. And you may think maybe it's peculiar to photons. But no, if you did the same experiment with electrons, the results would be identical. And you can even send bigger things, like large molecules, and they also interfere. So they go through the two slits. The technology to do the experiment with cats instead of large molecules is not yet completely at hand. You have to cool them to 0 degrees and things like that. But if you throw cats to the slits, eventually you will find an interference pattern of where the cats arrive. Now, this is a first unification of the very many that we shall see. That is, two different concepts, particle and light, are aspects of the same thing. Unifications are very important to science as we understand more and more things in terms of fewer concepts. Now, what are the properties of the particle of light called the photon? It's elementary. That means that as far as we know at the moment, it has no substructure. It doesn't consist of smaller things. Its mass is 0, which means that light travels at a velocity which is the velocity of light. That's not very surprising. The velocity of light is always called c. And it has spin 1. Spin describes, in a way, how the particle, in spite of acting like a point, might turn around itself. And particles whose spin is integer, like 0, 1, 2 are integer numbers, belong to a category which is called bosons. And bosons have the peculiarity that if you add them to a box, the box never fills. If you add them in the same quantum state, it turns out that it becomes easier to add the next one. So it's a very peculiar property shared by ghosts in a train car where there's always room for another one. Now, regarding the next unification, here it comes. You have two players of baseball. One sends a ball to the other. It gets an impulse back from the impulse that it gave the ball, and he gave the ball, and the other one collects this impact and goes backwards. This is an interaction mediated by the ball. If you have two electrons shown here as a line, the way they interact is by one of them sending a particle of light photon to the other one absorbs it, and that's the way the two objects interact. This is another unification in the sense that the concept of particle and the concept of force are intimately related. A force is an interchange of particles. And that's how you can have hydrogen, which is made of an electron and a proton, and bound together these two particles by the exchange of photons, these wiggly lines. But hydrogen can also be in an excited state and go to the ground state of a smaller energy by emitting a photon. So the photon acts as a force here and as a particle which is emitted here, although it's the same concept. So this is a unification I referred to. Force is a particle exchange. Now, I have already named another particle called the electron, which is also elementary. That is to say, if it has pieces, we don't know about it. And elementary particles are precisely the contrary of wine. If you have a wine from Ribera do Douro, or even a good one from Ribera del Duero, you need thousands and thousands of adjectives to describe it. I'm from the other side of the Douro, so I have to defend it. Everybody here is defending some small area of the world, Porto, Lisbon, etc. The electron is so simple that it only has 4 properties. Its charge in some units is -1, its mass in some units is 511, its spin is 1/2, and it has a cousin which is called the electron neutrino. And those are all of the properties of an electron. And all electrons share the same properties. And electrons, as I said there, have spin 1/2, which is a half integer. 1/2, 3/2, 5/2 are half integer numbers. Those particles that have fractional spin are called fermions. And they have the property, which you would expect, that if you put them into a box, the box again gets filled, and there's no room for another one. Now, let me open a parenthesis here to describe the concept of field. Field for a physicist, or more precisely a relativistic quantum field, that is to say one that obeys relativity and quantum mechanics, is the mother of all concepts. It describes, it's a function of position in space, x, y, z, and instant in time, t. If it is static, that is to say it doesn't change with time, then it describes an action at a distance, like a force. If it is dynamic, it expresses the properties of waves. If it is quantized, it describes also particles. And if it is demiurgic, it describes the creation of destruction of particles in certain processes. That's a very, very large unification. There's a field that encompasses our description of all fundamental objects. Let me close the parenthesis and go to the next transparency, which I have no idea what it is about. Yeah, it says that relativistic quantum field theories describe particles, waves, and their interactions. And they are equivalent, these theories, to Germany in the European Union. That is to say, everything not explicitly allowed is forbidden, and almost everything is forbidden, and in practice, nothing works except a very few things. Now, the best theory, which is a relativistic quantum field theory that we have, is called quantum electrodynamics, and it describes the interactions between particles with an electrical charge, which I call here E, can be an electron or any other one. The electrical charge is the ability of a particle to emit or absorb a particle of light, a photon. And the theory describes precisely and very simply how a particle interacts with light. The interaction is the current of the particle, called J. It is an object in motion, it has a charge, so it's a current, times the field of the photon. And with such a simple theory, we have a relativistic quantum field theory that works. An example of how it works is the following. An electron also acts like a little magnet in the direction of its spin. And in certain units, the intensity of its magnetism has a value 2 that was deduced on the basis of this object here by Dirac in 1928. But that's not a precise statement, because as it interacts with a photon, an electron can emit and reabsorb another photon as it does this interaction. And that corrects its magnetic moment by an amount which is alpha over pi. I'll tell you in a moment what this is. This was worked out by Schwinger in 1948. Alpha is the square of the charge of the electron divided by 4 pi, and as a number is roughly 1 over 137. So that this correction is about 1 in 1,000, small correction to the 2. Now, those of you who are paying attention are already thinking that you can do more things, like you could exchange 2 photons, like in these diagrams, to the so-called next order. And one of them is particularly interesting. Here a photon becomes a pair made of an electron and its antiparticle, a positron, becomes a photon again, and then interacts with this external electron. And the contribution to the magnetic moment of the electron via these 7 diagrams was worked out by Sommerfeld and Peterman in the late 50s. Those of you who are really paying attention have already drawn the diagrams to the next order, which, as you can see, are 72, and here they are. Now, what is the result of all this? First of all, the magnetic moment is 2 plus a correction, which is called the anomaly. The anomaly can be computed in powers of the square of the electron charge in the manner written here. The first coefficient was computed by Schwinger. The second is this beautiful number here, computed by Peterman and Sommerfeld. It took them 30 years to do it. It's not so simple. And then the third coefficient was computed analytically only another 20 years later by Laporta and Remedi. But the punchline is that the theory and the experiment agree in the value of the anomaly, the correction, to 3 parts in 10 to the 11. That is to say, the magnetic moment itself agrees between theory and experiment to 3 parts in 10 to the 13. 13 numbers that are computable and agree with experiment. This is what we physicists mean when we say we understand something with precision. We understand certain things with very considerable precision. Now, this is an estimate of the state of the audience as I am a quarter of the way through my talk. Now, you have all heard that something like your hand is mainly made of water, or maybe wine. Water is made of oxygen and hydrogen. Hydrogen is the simplest atom. It consists of an electron and a proton. The electron is elementary, but the proton is not. It's made of 3 quarks. 2 of them are called up, and 1 of them is called down. And there is another particle, 8 of them, for instance, in the nucleus of oxygen, called neutron, very similar to the proton, but it's made of an up quark and 2 down quarks. Now, things happen to these particles. For instance, if you have a 3 neutron, in a matter of minutes, it is going to, as time goes by, it's going to decay, and via a particle called a W, become a proton on one side, and 2 new particles that weren't there before. One is the electron, and the other one, since there is more than 1 neutrino, I have to give its name, is the electron neutrino. But one of the subjects that I will be talking about is this object called W in here, which we see in here acting as a force, the force that produces the decay of a neutron into a proton, an electron, and a neutrino, as in natural radioactivity. And that's called a weak interaction. And the W is a cousin of the photon. It's not an independent particle. It's a particle very much related to the particles of light. And something happened here, terrible. Yes. I have named some particles of spin 1/2, which are here. It's not all of them. This list on the left is temporary. I mean, there are others that I will not talk about today. I will talk about more the ones, that's a partial list, that are cousins or brothers of the photon. 2 of them are called W and Z. One I have already told you about, the W. The Higgs boson is another cousin of the photon. It's a manifestation of the photon. And one that I will mention towards the end is called the graviton, the particle that is responsible for the force of gravity. I will not talk about the other one, intermediate particle called the gluon, because I won't have the time. But let me go back to my main subject, which is unifications. Perhaps the most interesting one ever was made by Michael Faraday in the 1800s, and he proved that all electricities, he was an experimentalist, the best experimentalist of all times, are one and the same, which implied the existence of electrical motors, dynamos, etc., etc., etc. But what the hell did he mean by all electricities? We are so used to having only one electricity that we don't remember that Faraday had to demonstrate that frictional, galvanic, voltaic, animal, magnetic, and thermal electricity are one and the same. He liked the expression one and the same for some reason. He also proved that the forces termed chemical affinity and electricity are one and the same. So he is also the person who demonstrated that chemistry is just a piece of physics, the uninteresting part of physics. Now, the next remarkable unification was due to Maxwell, all these Englishmen, who demonstrated that electricity and magnetism are one and the same. And that implied that light is an electromagnetic wave. It's not something independent of electricity and magnetism. It's an electrical and magnetic field vibrating in space. That predicted the existence of other frequencies, smaller frequencies than that of visible light, like radio waves, or higher frequencies like X-rays, gamma rays, etc. And let me jump to the next unification. That is in the 60s and 70s, and it's due to Glashow, Weinberg, and Salam, who demonstrated that electromagnetic and weak interactions are one and the same. And this implied the existence of a particle, the W, which explains why the sun works and natural radioactivity, and why the reactors on this planet work so badly, and so on. And they also predicted that there should be another particle called the Z, which is very much like a photon, but with a mass which is not zero. It has a rather large mass. And this particle ought to mediate something which was by then an undiscovered weak force, very similar to the one mediated by the W, but different. All these particles, the photon, the W plus and its antiparticle, the W minus, and the Z, are intermediate bosons. They have spin 1, so you can always add one to a box. Now, in the 1970s, the pace of discovery became very, very fast, to the point that people writing newspapers had to write again and again about a new discovery. So they decided to save some time by writing a discovery matrix article on which they would only have to fill the details. So this is, for instance, the matrix article used by Le Monde. It's going to be in French. It says, scientific discovery. It has been announced yesterday that Professor such and such of such laboratory and Professor someone else, collaborators, have established the existence of new something. This is a discovery of great importance that proves the theory of someone who predicted that whatever it was, as a consequence of course, something else. And there's always another school of thought which interprets the new something as a manifestation of the very much sought whatever it was. Now, this was filled at the time by Lagarrigue at Orsay and Musset at CERN, demonstrating, and the collaborators, demonstrating the existence of a new weak force, great importance, etc., theory due to Glashow, Weinberg, and Salam, who predicted such a force, as a consequence of the unification of fundamental forces. And another school of thought interpreted the new something as an error of the competitors, because some people said it existed and some others said it didn't. Now, the W and the Z, which were the great predictions of the theory that unified electricity and magnetism and the weak interactions, deserved the Nobel Prize for Glashow, Weinberg, and Salam before the W and the Z were discovered. So this is the biggest risk that the Nobel Committee has ever taken. It gave the Nobel Prize before it was proven that the theory was right. Now, they turned out to be right because of another thing that was announced in the, this case, Le Monde, as Rubia of CERN and Dariola also of CERN and collaborators proved the existence of a new particle predicted by Glashow, Weinberg, and Salam, and it is due again to the unity of fundamental forces. And another school of thought interpreted at the time the new particles, which were the W and the Z, as a consequence of the very much sought Nobel Prize for CERN. This was the first one CERN got, I think. And it wasn't Rubia and collaborators, it was mainly Van der Meer who invented the technology to do the experiments. Now, the theory of Glashow, Weinberg, and Salam is so unified that the W and the Z are massless at the beginning of the story, like the photon. So there's a missing ingredient for the W and the Z to have a mass, as we know observationally. And that missing ingredient is called spontaneous symmetry breakdown. I'll talk about it for a second later. And it's due to a bunch of people, too many to quote, among them Higgs and Englert, who got the Nobel Prize for... no, I'm going to talk about spontaneous symmetry breakdown right now. Suppose you have a cup with this shape, and you drop a ball on it, it's going to be at the bottom. And realize that the system is symmetric. That is to say, it takes the same effort for the ball to move in any direction. There's a symmetry of rotations around the vertical axis. Now, if I take the ball and I put it in a cup with this shape, like the bottom of a bottle of wine, the system is still symmetric. All directions are equivalent. but little perturbation will make the ball fall on one particular direction, and that breaks the symmetry because now there's a preferred direction, the direction towards the state of minimal energy on which the ball is now. That's called a broken symmetry, and it predicts that there exists a particle called the Higgs boson, which is a neutral spin zero massive object called the Higgs boson, as I just said. And it's also a cousin of the photon. They are all intimately connected. Now, the Nobel Prize was given to Higgs and Englert after the particle was discovered a couple of years ago, and that means they had to wait 50 years for the Nobel Prize from the idea to the proof. Now, in the unified so-called electroweak relativistic quantum field theory, as I'm insisting, the W plus, the W minus, the Z, and the H are all siblings of the photon. That makes it palatable that I talk about the photon and its family. Now, I've been talking about mainly theory. Let me now move a little bit to experiment. There is an ensemble of accelerators at CERN near Geneva, which is shown in here. It's as complicated as a good Swiss watch of the old times when they were not electrical. And it's a very large complex. This thing has 20-something kilometers in circumference. And to it contributed a lot of people, not only the 3,000 people actually paid by CERN, but the so-called users. And I have in here a list of the users in 2010. Everything which is not white is a country that sends people to work to CERN. More than 10,000 in this transparency. Now, there are 133 from Portugal, thanks to the efforts of Gago. And from Russia, for instance, which is not a member state, there are more than 1,000. From the United States, there are fewer than Russians, but also close to 1,000. And if you look at a country such as Italy, which is not that much bigger than Portugal, it has 14 times more people at CERN. So there is something that they are doing a little better in the scientific point of view. This is the big accelerator. This is just magnets in the accelerator. I'm going to go very fast through this. And some points in this accelerator, which is also a collider of particles, holes are made, 100 meters deep holes, and big cavities are constructed. Cavities which you filled with the most sophisticated cameras on Earth, essentially a photographic camera, but a little bit more precise and complex. This is one of them being constructed as the central part is being put in the middle. And just for an idea, these are two people. This gives you an idea of the size of this camera. And these things are today's cathedrals in every sense but one. And that is tens of thousands of people collaborate, decades of their work to construct something which is as complex and as beautiful and slightly more useful than a cathedral. Now, surprisingly, these cathedrals are underground. And like this one, for instance, which is north of here, in Santiago. And the reason why these cathedrals are underground is that unlike the people who commanded the construction of these cathedrals, we physicists are particularly humble. So we put the cathedrals under, so that nobody can see them. Now, how does one of these things work? You take an atom of hydrogen and you strip it of the electron, you're left with a proton. You put the proton into something which is called a linear accelerator, and then you accelerate it to higher and higher energy in bigger and bigger circular accelerators, as in here. This one is 630 meters around. Then you send the protons to a bigger one still, where they have an energy something like 700 times the rest mass, and then they are injected in two different directions into a collider. This object is going to collide protons with protons. This is to give you an idea, a fake idea, of the protons accelerating through these magnets that guide that direction, while electrical kicks give them more and more energy. The proton is made of 3 quarks, and this is one flying towards a collision point. In a collision point, a proton coming from the other side of the highway collides in the middle of a detector, and what happens is what we call an event. Something happened, and new particles that weren't there before are being created and detected, scanned, and interpreted by this big camera, which is a detector. This is not the first collision ever. It's just one that I took at random because it's very beautifully reconstructed by the experimental apparatus. But this is the reaction of people seeing for the first time the first event, the first collision of two protons in their experiment. And you see that this is very much, well, first of all, you notice that Angela Merkel is there in the middle. And then you also notice, this is very important, that everybody is very happy, except these two guys on the right who worked all night so that the thing could start functioning. Now, what does actually happen in one of these collisions? You have two protons that are made of three quarks. They are coming together to the point where they collide. In some of these events of collisions, a quark emits another particle. This is the one I'm not talking about, which is called a gluon. And through a loop of quarks called top quarks, they produce a particle that wasn't there, for instance, a Higgs particle, that decays through another loop into two particles that you observe in the detector that are called, in this case, two gamma rays, two particles of light. And all the rest of the particles make a mess around, but among them there is this very interesting discovery that maybe you made something new. And that's the very act of creation. These things were not there before. They were woman-made or man-made. Now this is an actual event which is a candidate for a Higgs decaying into two photons whose energy is depicted here. Now from the energies and directions of the photons you can reconstruct the object that probably decayed in the two of them and find very many at the same mass, and that's the discovery of a new particle, in this case a Higgs, via decays into two gamma rays. Now once you extract the needles called H from the haystack, you find that there is something producing these events, and that something, a very simple thing, is also an elementary particle, presumably, and unlike Dupont and Dupont, all elementary particles are identical to each other. If you have two Higgs bosons, they are absolutely identical. If they have a moustache, it's not different, like the moustache of Dupont and the moustache of Dupont with a T, like the trait of the moustache. This is an estimate, again, of your status at we are, is this going to work? 3/4 shoot. Through my talk. Now, I'm now going to ask a really deep question. Suppose you have a room. I won't learn, there's nothing to do. Suppose you have a room filled with people such as this one, polite people, the ladies in front, the men in the back. And very politely also I ask you all to leave the room. And then I take off the lights, I take out all the air in the room down to the last molecule of nitrogen or oxygen or argon. I cool the walls to 0 temperature, so there is no thermal radiation. I have made a piece of vacuum. And interestingly, the vacuum is not empty. It is a substance, as we shall see. A substance in the same sense that there are substances that I am very, very well aware of, but I cannot see. For instance, here there is a gravitational field of the Earth, and that's why if I use my spectacles, I'll find them on the floor. There is something that permeates this, it's called the gravitational field of the Earth. If I go very far away with this empty room made of vacuum to a place where the gravitational fields are negligible, it turns out that there is still a field that permeates the whole universe, outside and inside you, and the vacuum not being a substance, its field is filled with a field which we call phi for its value on the vacuum, which we call 0. This means not equal to 0. That is to say, something permeates the entire universe. And it is thus something that I was talking about when I drew this diagram. This is the value of the Higgs field, and this is its potential energy of interaction with itself. It is now in the current time of the universe lying somewhere which is not the place of equilibrium. And its value is what I called in the previous transparency phi 0. And phi 0, the fact that the universe is permeated by this substance, means the following. It means, if I can go back, that if I throw a particle of a certain energy and small mass through the vacuum, it interacts very little with it. And that's why its velocity was rather fast. If I now send a particle of a bigger mass, it interacts more with the vacuum, and at the same energy, it travels more slowly. That's the origin of mass, the interactions of particles with the substance of the vacuum. Now, if the vacuum is a substance, you can shake it. This is very much like you do not see the air through which I'm talking to you, but you know that the air can vibrate as sound. If the vacuum is a substance, you can also make it vibrate, and its vibrations are elementary particles. The Higgs, this particle that was recently discovered, is a vibration of the substance of the vacuum. And if we were elegant, we would call it to kenonon, from kenon in Greek, which means vacuum, but for some reason it's called the Higgs. And the LHC, an object that means Large Hadron Collider, of which I showed you pictures before, is actually a machine to shake the vacuum. This is the best thing it has done so far. Now I must issue you a warning, very serious warning at this point in time, and that is this one in here, which I won't even pronounce. Now, let me go back to the photon and its most interesting recent manifestation, which is the discovery and analysis of the cosmic background radiation. Now, this is the universe. It is expanding, as you can see. As it was expanding, I took a video of it to see what was going on. Then I pushed this button to stop the video. Then I study what is in the universe and understand how things work, what particles there are, and what their interactions are, and so on. And then I push this other button, and I go to the past, now understanding what happened as the universe in its past was more concentrated. And that is shown in this transparency, which is almost 40 years old, and it happens to be in Spanish. The main thing to realize is that as time goes back, the universe was more concentrated, and therefore it was hotter. If you concentrate a gas, for instance, it gets hotter. And this is this line of the temperature of the universe diminishing with time if I go forward in time, and going up if I go backwards. I'm going backwards, so I have to tell you that very recently, in cosmological times, the last dinosaur died. This happened on the 20th of December of 1975. The name of the dinosaur was Generalissimo Francisco Franco. And we all thought that this was a definite extinction. It turned out not to be the case. They are still around in politics. Now, as you go back in time, there was a very interesting moment at which the temperature of the universe was 3,000 degrees. At that time, the light of the universe and the atoms of the universe collided so brutally among each other, because temperature is a measure of energy, that they dissociated into protons and electrons. If you go backwards in time to the age of the universe of about 3 minutes, then the temperature was 1,000 million degrees, and the nuclei of atoms, such as the nucleus of helium, made of 2 protons and 2 neutrons, collided so violently that they split into protons and neutrons. And with the experiments that we have done at accelerators, we can go back in understanding with confidence the history of the universe up to a time when its age was at a temperature of 10 TeV, studied at the LHC, 10 to the minus 15 seconds. So it's a rather young universe. Now, if we look forward, then we have the predictions of how many elements were made when the universe was this old, and those we can measure, and they agree with the theory. And we can also go and understand the properties of the microwave background radiation that was emitted when the universe became transparent to light in this transition here. Now, if we look at this light, the microwave background radiation, we can say things with certain confidence, only certain confidence because we haven't tested them experimentally in a different manner, from the time of inflation, when the age of the universe was about 10 to the minus 36 seconds, very young. Now, the cosmic background radiation is this thing in here. Was this thing in here? Sorry, we have to go through all this again for some reason. Come on. Okay. This is a picture of the night sky going in all directions, plotted as an ellipse. And what you see are regions that are slightly hotter and slightly colder by 10 in a parts in a million degrees. So very, very small differences in the temperature of the light that comes to us from everywhere in the universe at a distance of about 13 billion years, light, which is the age of the universe, coming to us at the moment, seen in all directions. So this is the true picture of the night sky. Surprisingly, the theory predicts that these things here, hotter and colder, and denser and less dense, are quantum fluctuations. When the universe was 10 to the minus 35 seconds old, it was so small that quantum mechanics meant that there could be fluctuations in its energy density. These fluctuations have grown to the size of the universe that we can see now and are still seen here. So the biggest things we can see are quantum fluctuations, not only the smallest ones, of the energy density of the baby universe. Now, when you analyze these fluctuations, you get this curve in here that I will roughly explain. You look at how much excess of energy there is at a certain angle, for instance 1 degree, and the fluctuations are very large, they are this big. And then at 1.5 degrees or whatever, sorry, 1/2 of a degree, there is not so many, and there is another smaller size at which the fluctuations are also important, etc., etc. This looks like harmonics. They are actually harmonics of these vibrations. Now, if you listen to a scale of music, such as this one, you can immediately tell it was a violin and not a piano. The reason why you can tell that is that the harmonics are in certain proportions to the main peak, and that's what tells you which instrument you're listening to. Precisely in the same manner, the analysis of this curve in the previous plot shows you the composition in terms of energy density of the entire universe on average. It has a little bit of matter, like 4%, what you are made of. Then there is another kind of matter of which there is 5 times more that we know is matter made of objects similar to particles, elementary or not, but we don't know what they are because they don't emit light, these things. And then the rest is the energy density of the vacuum. Again, the vacuum playing a fundamental role in science. It is the simplest object, the least well understood, and the most important. Now, that is, as I just said, the energy density of the universe in terms of the vacuum. So just to conclude, I'm telling you so far the things that we understand. One has to confess those which we do not understand. We do not understand the energy density of the vacuum. We do not understand gravitation as a quantum theory, only as a theory before quantum mechanics. We do not understand the relation between gravity and the other fundamental forces. And in that position, we are precisely where Faraday was in 18-something, 30 or so. He was the first one to try to unify electricity and gravity. And he was an experimentalist, so he did it experimentally. He dropped balls by releasing a string. People who do these things now use something called a superstring. He used a normal string. And those balls fall on a cushion and they decelerate. And he hoped that deceleration would emit a wave that he could see electromagnetically by inducing a current in a galvanometer. He thought that there was a relation between electricity and gravitation that he could discover experimentally. Now, he was not only the best experimentalist of all times, but also perhaps the most honest. And he wrote in 1850, "Here end my trials for the present. The results are negative. They do not shake my strong feeling of the existence of a relation between gravity and electricity, though they give no proof that such a relation exists." So he was convinced, but he failed, and he admitted. And I think in this moment of humility borrowed from Faraday, this is a point, and I think it's a good point to stop. Thank you very much. I suppose it's time for questions, and I seem to be the chairman of the session.
Okay, we are open to questions.
The chairman was sleeping. I apologize for him.
He's not said that he gave all the questions.
I wonder if you could clarify something which may have left some people a bit confused. Many of us were taught that Einstein and his contemporaries abolished something called the ether, which was a substance which was to fill the vacuum, and people had been talking about it for thousands of years. Now you're telling us, are you, that the ether in some sense is back?
Yes, very good question. And it is indeed back in some sense. The ether of pre-Einstein days was the substance of space. And it corresponded to a fixed space on which things happened. And as you mentioned in your talk, Einstein realized that that space was fake because light travels at the same speed in any reference system. So the classical ether, which was a system of coordinates anchored to the vacuum, was killed by Einstein. Now, the ether that we're talking about, the substance of the vacuum of the actual universe, is a field of spin zero. And it has a property that you couldn't guess, and that is it looks the same from all reference systems. So this particular vacuum, and no other, is relativistically invariant, and is not the ether, in that it is not defining a fixed system of reference.
Are you satisfied?
Thank you for your nice talk. I don't know if my question is stupid, but I am human. And when in the cosmic time that you mentioned appear our light, I mean a wavelength of 4,000 angstrom, 400 nanometers to 700 nanometers is our light, 400 to 700. When does it appear?
It appeared when the universe was 380,000 years old. At this point in time, light was emitted at 3,000 degrees, which is similar to the temperature of the surface of the sun, which is 5,000 or something like that. So the first visible light appeared when the universe was this old. But meanwhile, the universe has expanded by a factor of 1100, And that means that the wavelength of this light, which is the cosmic background radiation that I talked about, has been stretched with space by a factor of 1100. So we now see it as microwave background radiation at the temperature 1100 times smaller, which is 2.7 degrees absolute, which is the temperature of the microwave background radiation. So the light was there, but it got stretched with time. If you have lived when the universe was 500,000 years old, which you couldn't because there weren't galaxies yet, if you happen to be there, you would still see the light that you see today. But that light has been stretched away to the invisible part of the spectrum. Now, galaxies emitting real light appeared soon after that, maybe when the universe was 1 billion years old or so.
One more question.
Why physicists, or is there any necessity to unify gravity and the other forces? Do physicists can't accept gravity and the other interactions as a separated phenomena?
You see, it's a question of success. In the past, every unification has implied a very important step forward in our understanding. So we hope that the pace of progress continues along this line and that things are more and more simple and unified as we understand them better and better. We can be right or we can be wrong, but why should we be wrong?
Okay, thank you, Alfred. You have been enlightening.
I have a present for you.
Ah, thank you very much.
Well, it's not a present. It's just to show you something that we did in a science cafe about the Higgs boson at the parliament here in Portugal.
Thank you very
with
much.
The photon and its siblings.
Thank you very much.
This is to give you some homework too.
I have to reconstruct it. It won't be easy.
No.
But I'll try.
Thank you.
You very much.
Olha, muito bom dia. Vamos então, let us continue this session now about cosmic light. So, cosmic light, the light from the stars, the light from heavens, is one of the main topics in International Year of Light. And to talk to us about this topic, I have the pleasure to have here with me two Portuguese physicists, Portuguese astrophysicists, although Pedro Russo is at University of Leiden. Pedro Russo is very well known as he was the commissioner, the president, the coordinator of the International Year of Light in 2009. And, astronomy. I'm sorry. So we were then dealing just with cosmic light, of course. And he has won a prize about his project of universe awareness, a prize of outreach and education by the European Association Scientifique about education and outreach. He now is leading one major program in Horizon 2020, again about outreach and education in space and astronomy. And André Moutinho is the Portuguese coordinator of he's coordinating the Portuguese participation in the Gaia mission, which is a mission from the European Space Agency to map the stars and galaxies. Okay. He and his team developed a visualization scheme enabling to deal with lots, billions, zillions of data and producing beautiful visualizations of the cosmos. So please, Pedro, take the floor, and then André, and then we'll be able to ask questions to both the speakers.
Obrigado, Ana. And thank you everyone for being here. It's almost lunchtime. We'll try to be short and to have some time for some questions as well. I'd like to start actually my talk by also pay homage to Mariano Gago. I started my university studies more or less at the same time when Mariano started as Minister of Science and Technology in Portugal. And I think he provided a lot of resources, means, even a framework to modernize science in Portugal. But to me, he gave us hope. Hope to be scientists, hope to be engineers, and particularly in my personal case, he gave me hope to follow a career in science communication by putting Ciência Viva at the core of his policy for modernizing science in Portugal. So I'm extremely grateful for that, and I follow a career in science communication a lot thanks to Professor Mariano Gago. I'd like to give my talk about light and astronomy. Like Anna was saying, the International Year of Astronomy was very much about light. We astronomers, we use light as our raw material. It's essential for us. It's with the night sky, it's with the light of the stars, the light that bounces in the planets, that we fully understand some of the things that the previous speaker talked about the universe, about the Big Bang, the origin of the Big Bang, of the universe. We also understand how stars form, how they live, how they evolve, how they die. And some of the stars die in beautiful shapes, like this planetary nebula here. It's a beautiful image of a Helix nebula, and it's one of the ways that the stars die. And we understand that by using light. We also find planets around other stars, what we call exoplanets, these amazing worlds that we know that are outside our solar system. As today, we know almost 2,000 exoplanets. The first exoplanet was found in 1995. So in the last 2 decades, we found brand new worlds. And maybe some of these worlds will be very similar to our own planet, and maybe they even have life. And it's through light that we're going to find life in these planets. We also understand that we live in a galaxy, the Milky Way, our own galaxy. It's through this light that reaches our telescopes that we can find and discover and study galaxies, how they form, how they evolve, how do they rotate. And it's through that rotation that we know that dark matter exists. And it's really, astronomy plays a big role in the science of light. But we astronomers are a bit less humble than the physicists, and we build large cathedrals on the top of the mountains. We like to show off, so that's why we build large telescopes like this one in Chile, in the Atacama Desert, a consortium of European countries. They got together to build these massive telescopes. We have 4 of them that we call Very Large Telescope, and it's through these telescopes, advancing technology. We use cutting-edge technology, cutting-edge detectors of light that we really understand how the universe works. But we astronomers, we have a problem. We cannot, most of the times, we cannot go to objects that we study. We cannot go to the stars. We cannot go to the galaxies. We have to collect information as much as possible. And we collected this information through light, through the visible light, the light that we see, but we also need other forms of light, like radio light, radio waves. So that's why we also built radio telescopes to study the objects in a completely different light from the visible light. We study them in radio. We also try to defeat the atmosphere. The atmosphere disturbs a lot our observations. And for that, we need to put some telescopes up in the space. And this is one of the most successful projects in science. That is the Space Telescope Hubble. That was a collaboration between the NASA and the European Space Agency. And it's still working after many, many decades working in space. So here is the reason why sometimes we also need to go to space. This is shows pretty much how transparent is our atmosphere to certain forms of light, starting from gamma rays. And if you see the brown part, 100%, it means that gamma rays and X-rays, for example, don't reach our atmosphere. And that's a good thing, because it's because of that that we have life in our planet. We have some windows where light goes through. The light of the stars, invisible light, reaches our surface, and the same with radio waves. But sometimes, like in infrared, gamma ray, and X-rays, we need to launch satellites and put the telescopes up in space to capture all this light coming from different wavelengths. That's why, for us in astronomy, it's super important to have space astronomy, to launch satellites, to collect light in these different wavelengths. So this is an example of how big are the telescopes and that we are building and we operate. There you have the Arc of Triumph in Paris for comparison. And there you see the 4 telescopes that are operating in Chile by the European Southern Observatory that are the very large telescopes. At the moment, we are starting the construction of a big telescope called Extremely Large Telescope. We go from very large telescope and extremely large telescope. We like big telescopes, but we are not very creative with our names. And these telescopes will be able to observe directly these exoplanets that we are finding now. So we're going to see directly these exoplanets, and that's going to be a massive breakthrough in astronomy. And we are really looking forward to have these telescopes working and operating in the near future. We also, again, put telescopes in space, and this is going to be the successor of the Hubble Space Telescope, the James Webb Space Telescope. And we are building also large radio telescopes. This is the project called Square Kilometre Array, and it's been built at the moment in South Africa and Australia. This telescope is more than just a science project. It's a lot of development project. By establishing these telescopes in the southern part of Africa and engaging a large part of the countries in the southern part of Africa, we're going to provide infrastructure, we're going to provide skills, we're going to provide knowledge to these communities. And this is a truly development project by using astronomy for development. And we are extremely proud of this project, and hopefully it's going to be fully operating in 10 years' time. And we are now building these telescopes in South Africa, southern part of Africa, and also Australia and New Zealand. But there's a problem. These telescopes are going to create large amounts of data. And data in astronomy means collecting all these photons coming from the universe. So SKA is planning to produce, after the duration of the project, the equivalent to 10 times the current global internet traffic. That means that it's going to create an enormous amount of data. And that's a big problem. We're going almost from big data to mega data. That's more than the current daily internet traffic around the world. So we need to develop new technologies. We need to develop new tools. And for that, companies like IBM are already working with the project, trying to figure out how they can solve this data problem. Because in the future, if we think that this astronomy is going to create large amounts of data, I'm sure that the internet and the way that we consume data is going to increase as well. So solving some problems that we have in astronomy now might solve some of the communication problems that we're going to have in the future as a society as a whole. So again, astronomy is pushing the boundaries of technology on data processing. And in this case, is the way that we process light. The same with the space telescopes. The mission that the European Space Agency is working at the moment, called Euclid, to map a lot of this dark matter that the previous speaker mentioned, it's going to create around 850 gigabytes of data per day. That's a lot of data per day that astronomers have to go through, that we need to analyze these data. So there's a lot of challenges on that, and I'm sure that André is going to talk a lot about what we are already doing to solving some of these issues in astronomy. So for astronomers, large amounts of light, and we're going to have a large amount of light, means big data, means actually mega data. It's going to be really massive numbers of light. There's several challenges. How we can visualize all this data? How can we make this data in these beautiful images that we have from the universe? What kind of algorithms and softwares we need to develop? And what's going to be the technologies like machine learning, like Google is doing and Amazon is doing, to go through this data and get knowledge from this data? It's a challenge for astronomy, and we are working on that. And in my particular case, I'm really interested in finding ways, how can we engage the society, the known experts, with these large amounts of data? What can we do? How can we make sure that society as a whole can benefit and contribute to understand better our data? And there's already some projects on that. Galaxy Zoo is a good example. We have large amounts of data already now in astronomy, and a group of astronomers are creating citizen science platforms where they ask the public to help going through these images and telling us, what do you see here? It's a very simple platform. We can say, this is a galaxy, this is not a galaxy, this is elliptical galaxy, is a spiral galaxy, what is the shape, what's the color, etc. And that provides meaningful information for the astronomers. It's called people-powered research. We ask the society to engage with our research, citizen science, and that's a way that we can involve citizens with large amounts of data. We can do that for discovering new exoplanets. We ask them to go through our light curves and try to see if they find planets. Or even with the Higgs Hunters is another platform that they look at the data from LHC and help physicists to find new particles. All this is already available, and people can already engage with large amounts of data. So, but we know that astronomy is part of our culture. Since the beginning of times that we have been trying to understand the mechanics of the universe. We have been keeping record of that. We keep timekeeping, like for millennia we're going to be doing that. We even use astronomy for celestial navigation. We even understand the way that the world works through astronomy. But we have a problem, also for astronomy and also for society. It's called light pollution. There's more and more people living in cities. Even in the dark spot, like in the Azores, you can already see the bright glow of the cities. And we are losing this connection with the Milky Way that you can still see there. We are living in cities, and it's expected that in the next 10 years or even 20 years, more than 70% of the world population is going to live in cities. And these people are going to lose the contact that we have with the night sky. Most of the people that live in cities, they don't know what's the Milky Way. They haven't seen the Milky Way. And I think this contact with the sky, that is part of our cultural and natural heritage, we are really losing that. And there are several impacts on that, of course, in the nature. Some animals, they lost track where they have to go because of the light pollution. And even for humans, there's some research done on the light pollution as a risk factor for the humans. And a lot of publications have raised this issue, that we are losing a lot of this contact that we have with the night sky, like the magazine National Geographic a couple of years ago. Some natural parks are providing some guidance and asking people to come and use the night sky as part of that natural heritage that the natural parks have. And these are just posters from the natural parks in the US. So that's why the United Nations, in their resolution to make in 2015 the International Year of Light, mentioned that the reduction of light pollution, which is key to the preservation of dark skies, as one of the most important things. And in this year, the astronomy community has been working on that under the Cosmic Light Project. You can find a lot of information about that. And it's because of that that Saturday we are organizing the Dark Sky Reserve in Alqueva, just 2 hours away from here, from Lisbon, a series of activities, public talks in the afternoon, night sky observations. We're going to open an exhibition, and everyone is welcome to join. There's a free shuttle, actually, from Lisbon to the museum, return trip. So you should definitely join. And we're going to have some things in English and some things in Portuguese for sure. So everyone is welcome to join and to see the Milky Way, see our Via Láctea, maybe for the first time. Thank you.
No, I would suggest that we keep our questions. So if you have questions for Pedro, please take note, and we continue immediately with André Moitinho from the University of Lisbon.
Thank you. Good afternoon to all. So I will take on after Pedro, and I will talk to you a little bit about the challenges in visual exploration of large multidimensional astronomical archives. Pedro has already given you a kind of an overview of what was involved, and I will go a little more into detail. But I will focus on the case of the Gaia mission of the European Space Agency. So first, I will start. The talk is divided in 3 parts. I will give you a context, then I will talk to you a little bit about Gaia, and then about visualization of these databases. So the context of the mission is the Milky Way. Pedro just left the last slides with the Milky Way, so it's a happy coincidence that I start with that. This is an image of the Milky Way seen precisely over the Alqueva. Usually when I used to give older talks, and I talk a lot about the Milky Way, it's my scientific subject. I used to search Google, I used to Google and write Milky Way and find these really nice US National Park photos of the Milky Way with cactuses and all that, but not the kind of scenario you see in Portugal, not the kind of landscape. And one day I had the brilliant idea, what about if I search Via Láctea? And of course I was missing these beautiful images of the Milky Way right here in Portugal. And in fact, here in Portugal, we have some of the best astrophotographers in the world. Several of them are Portuguese. This picture, for instance, was taken by Miguel Claro, a very well-known name in international astrophotography. So I start with this image. Well, the Milky Way, you can see this band, is in fact, we know today, a galaxy. It's one galaxy within a wide variety. We usually talk, I think I lost, no. Can you hear me? Yeah. Within a big variety of galaxies, all with different shapes. Ours is what we call a giant spiral barred galaxy. It could be somewhere around this part, but we could also argue it's a bit more intermediate. But anyway, we're not going to care about the details of the Milky Way right now. What we will focus on is that the importance of studying the Milky Way. Well, we can see many of them from far away, and we can see their details, well, we can see their shapes. We cannot do that on the Milky Way. If we just go back, we see that we just see this band. We cannot see it from the outside. While we do, and we can see all the rich shapes of the others. However, since we're in it, it's the only galaxy we can see in detail. We can really, I will not describe this image as a whole, but it's an image I use a lot. It's impossible to overstate the enormous amount of astronomical information this single image has. Just to let you know, it shows a complete cycle of contraction of the interstellar medium into forming stars, into forming disks around stars, and even to stellar death, all in the same image. And these are the kind of things that you can only see in the Milky Way. So if you want to compare the study of the Milky Way to the study of external galaxies, it's like trying to study animal biology, in which you can see, well, all the horses or zebras or whatever at a distance. You will learn a lot about these animals. But then if you want to look into the physiology and into the way they work inside, you must look at the cells. And here we are looking at the cells of galaxies. But of course, we are inside, and we can have access to more detail, but only if we could determine the distances to these objects. Now, Pedro already mentioned that all these things are very far away. We cannot go there. We cannot reach these objects. Well, we can reach a few in the solar system. So what kind of ways can we find to get information out of the cosmos, of the universe? We usually call these what provides information to us, the messengers. So what are the messengers of the universe? Well, it's mostly light, really. That's what we use 99.999% of the times. But of course, there are others. We do gather information from cosmic rays in certain situations, from neutrinos, if you just can detect one, and we hope that one day from gravitational waves. Well, it turns out that although we cannot go there, there is a way we can determine in a fundamental way the distances to astronomical objects. We can use this effect called parallax. Now, we experience this effect on a daily basis. Just imagine you are in this point A, you look at a tree, and you see that the tree is projected against the background object in a certain direction. Now let's just move to point B, and we will see that the tree is projected against the house. So this tree moves according to the distance it is from me. The further away, the less it moves, and according to the baseline, the distance from A to B. If A and B are further away, I will see a bigger change in the position. If they are closer, I will see a smaller one. It's harder to detect the effects. But with this, we just have to solve this triangle, and we can determine the distance to that tree C. Well, how does this apply to stellar distances? It turns out that we live in a spaceship. We're in the Earth. And so we can move from point A to point B by, well, waiting for the Earth to go around the sun every year. And you can see that in June, for instance, you will look at a star and you will see it projected against further points and at a certain position. And you will see on the top panel over there the June view. Do I have a pointer or something I could use, perhaps? Oh, yeah, there's one here. Okay. You will see here the June view. Well, just wait 6 months and you can see the position in December. And you will see the star projected against other objects. And you will see it changed against objects that are very far away. And with this change in positions, which we call the parallax, well, actually this angle is twice the parallax, but that's a technical detail, we can determine the distance to the stars. Why? How? Well, we know that we can relate this side to this angle and to the distance from the Earth to the Sun. And the distance from the Earth to the Sun is something that we can determine very easily. It has been done already since old times, for instance, using the transit of Venus, or in more modern times, even with radars, that we can point not to the Sun, because the Sun will absorb the radar waves, but we can find the distances to other planets like Mercury or Venus, and from that we can find all the distances in the solar system. That's a different talk. I'm not going to spend my time right now on that. Of course, it's not so simple. All the stars in our galaxy are all moving around the galactic center. They could not be stopped. If they were stopped, they would just fall into the galactic center. So they need this force, this apparent centrifugal force, to make them to make the galaxy stable. So they're all moving, and they're all moving with different velocities. So with time, these stars, let's see the Big Dipper today, but each star has a peculiar velocity, and in a few years, well, not a few, in 50,000 years, it would look like something like this, a bit different. So if the stars move, we will have to take this effect into account when we wait the 6 months. So in fact, we will have to determine not only the position of the star, but also the movement. So we will have to measure this several times so that we can solve the equations for both. Just a factoid, the Sun moves around the Earth, the galactic center, at 220 kilometers per second. So everything is moving, and moving quite fast. 1, 2, 3. I'm in Madrid right now. So it's really, really quick. Okay, but there's also another issue. As Pedro said, we are limited by the atmospheric turbulence. So if you want to measure position very precisely, and you saw that the further away the star, the smaller the angle. So if you want to measure stars that are reasonable far away, you need to be able to measure very small angles. And so, but that is very hard to do in the atmosphere because we have the turbulence, and try measuring the position of something out of focus and moving all the time. It's irritating, to say the least. So this is why we go to space, in the case of Gaia. And I'm going to talk to you about mainly Gaia, but it has its predecessor, which was the Hipparchus mission, which was launched in '89 and it did in '93, although the final catalogue of stellar positions was only produced in '97. And now the mission that is ongoing, which was launched in December 19, 2014, and it will end around 2021 or 2022, depending if we get an extension or not. So, in a nutshell, well, this is an image of Gaia before being launched. Now we cannot see it anymore. It's too far away. It's 1.5 million kilometers from the Earth. It's quite far, although that's only 1% of the distance of the Earth to the Sun. And so, what is the objective of Gaia? Well, it's going to determine positions, distances, motions, and then several astrophysical quantities for around 1 billion objects. To get these very precise distances, to measure these triangles really well, it's going to achieve something that is completely unimaginable. It's going to try to achieve a precision of about 7 micro-arc seconds in accuracy, not precision. You know what this is? It's so small. Well, a circle is divided in 360 degrees. A degree is something like this. This is divided in 60 minutes, which is something small. If you divide this in 60, you get an arc second, something really, really tiny. Now divide that by 1,000,000, and you get the micro arc seconds. So it's so small, an angle so small, that it's equivalent of measuring the thickness of a hair of someone that is about at 1,000 kilometers from us. Like, you can see the thickness of a hair of someone, let's say, further than Barcelona. Or the nail of someone that is on the moon. It's absolutely astonishing. And it's going to be done for around 1 billion objects. This will generate an archive of around 1 petabyte. And the objective, of course, is to do science on the Milky Way. This is a technical slide just to say that this is possible. It's not something easy. It has never been done before. We are trying to demonstrate that it's going to be done. We think it's going to be done. Let's see when all the data is here and we have processed it. But we think it's going to work. And one of the things that makes it possible is that it has the biggest focal plane. The focal plane is where the detector of the camera is. So you have a small photographic camera, usually have a small CCD or a film. This one, the film, the CCD, where the image is formed, is in fact an array of about 1 meter by half a meter. It's an enormous thing, and you will be seeing stars all the time. It's really something incredible. And to give you an idea of where we are, so this is the position of the Sun. This is the galactic center. And this is about the distance we will be able to measure with a reasonable precision, accuracy, the distances to the stars with Gaia. And this is, even on the other side of the galaxy, the radius until where we will be able to measure with good accuracy the velocities of the stars. So positions and velocities are essential for doing all the dynamics, for recreating the history and evolution of the Milky Way so that we can see really internally how a galaxy works. And there are many, many other things. One important thing is that with these positions so accurate, they will also define the absolute reference frame that we use in all our measurements. So when we want to know where we are for navigation, we use stellar positions. In the past, sailors, navigators, explorers used the stars to navigate. Today, what do we use? Well, perhaps people say, well, we use, let's say, GPSs, which are better. Well, it turns out that the GPSs, they do not know where they are unless they look at the stars to see where they are. All these satellites have this device called a star tracker. And these star trackers take images of the sky and references these images to catalogs. The more precise, the better. So although we use GPSs today for navigation and positioning, we are essentially still navigating by the stars. Okay, since we've been working on Gaia, it was unavoidable to organize a Gaia meeting in Villanova at Gaia. We just could not resist it. And this was featured as an ESA picture of the week for the Gaia mission. For the people that do not live here, it's just across the Douro River where they have all the port wine cellars, which was also a plus. This is another image of the week concerning the theme of visualization, and we have been featured more times. So, what are the visual exploration challenges for the Gaia mission and other big data, especially in astronomy? Well, first, it is interesting to notice that humans are, above all, visual beings. The neural substrates serving the visual sense occupy about 30 to 40% of the cerebral cortex total area. So we have a lot of our brain put into visualization. It's not surprising that it is visually that we can often transform the overly complex into something that is more humanly graspable. Our brain is really putting a lot on work on that. And visualizing things is frequently the starting point and even the guiding reference for scientific and even other kinds of thoughts. And Pedro already showed you some ancient pictures of ways people organize visually information. I have here a few more. Well, this is the older known lunar calendar, and then we have a time series of planetary orbits, just to show that people have been visualizing astronomical information and keep storing it for a long time. Well, in the petabyte scale visualization, there are challenges. The first one comes from the physical sizes of the archives. The hardware resources for this, for storing all these archives, are enormous. And it's not only the size of the computer, the disks, and the RAM, but also the bandwidth. If I want to access these data, I need a lot of bandwidth so I can transfer data from one side to the other. So this leads to usually client-server architectures. I have something that is running close to the data. For instance, my data crunching algorithm, my number analyzing, my machine learning algorithm or whatever, which is close to data, and then just sends me something out, which is, let's say the result of this is nothing more than a simplified version of the data. Of course, if we want to do this exploration and data analysis interactively, which is the way we get more and more used to, because exploration is an interactive process, it will bring me extra difficulties, mostly on the hardware side. And then there is also challenges in the analytics. We just have too many data to represent, too many dimensions, too many interrelations in all these high dimensions and all these points. And if you just try to plot 1 billion points on a screen, you'll just see everything white. You get just data stuns. And this is a big problem. Okay, there are many techniques to solve the hardware problems. For the data stunning, well, one of them is just what you see in Google Maps. You just get detail on demand. When you zoom in, you get a smaller field but bigger detail. And this can be done in 3D. And there are many other techniques, like using transparencies, lenses, and all that. I'm not going to go more into detail, but these are things that we have been working on. One of the things that is really important is that when you have many points, sometimes an extra dimension really makes a difference. Representing data with 3 dimensions instead of 2 sometimes just makes points pop out. This is not very used when doing exploration with point data because of the way of interacting and selecting point data in 3 dimensions is really a problem. Usually just see 3-dimensional analysis when you use extended bodies like fluid simulations or CADs for extended bodies like in medicine, etc. And so now I'm going to show you a small 3-minute film which illustrates some concepts, some work we have been developing on this subject using a technology that was used for being very highly interactive for producing games. And so I will show you to you right now. Pedro, do you have it? Where? Ah, puseste o vídeo aí, está bem. Okay, sorry. Okay. This is a project called CSI Vega, which is, well, it has this name. We like to invent license, just to show to you, which was a project that just ended, which is a concept study for an interactive visualization environment for the Gaia archive. I told you we focus on 3D visualization, and we use technologies that are built for developing games. In this case, we're not using the big data set, a big Gaia simulation, but instead we're using the Hipparcos products. Hipparcos was the mission, the ancestor of Gaia, and so it's the same kind of 3D data. It's not the big data, but it's already useful for trying stuff with interaction in 3D. Now, this is just displaying data in a plane. Well, we can activate coordinates. This is something for, it's a workbench. It's not a working software. We can overlay catalogs. We're testing ways to interact with 3D data. Now, see how things pop out when you start in 3D. Everything was flattened. Once you start moving, you see structures from the data that were flattened and were cluttered. You see them popping out. Now, of course, we tested some. This is already more than 1.5 years old. We now use another platform for developing the visualization client. But see how stars that are related together seem to stay close to each other, while stars that are further away, they just leave. So an extra dimension really helps in finding details in lots and lots of data points. This is the Hyades, a very well-known star cluster, and this is the Pleiades. Well, this is the Pleiades data in the Hipparcos catalog. The Pleiades have more stars. One aspect for exploring many dimensions is that you can usually not see 12 or 13 or 20 dimensions in just one panel. You usually want several panels with different projections of the data in different axes. And you would like to identify a point in one panel and see it in the other panels so that you can see, you can feel the high dimensional relations within the data. And here we see how this can be done not only within an application itself, but between different applications. Sorry, Pedro.
Andre,
Wait.
maybe
I'll just put it to. It's just it's the end, really. Okay. It's 50 seconds, I think. One of the things we have been using this is for also applying it to watching space debris. You know that the Earth is surrounded by corpses of space missions and satellites. And so we have been working on this issue too, using this infrastructure for the analysis of space debris. And okay, we can stop here. I just wanted to show this use of the framework.
Thank you. Now, questions, please. From these two short interventions, we could have be talking hours. So, but I believe that the speakers can answer to some questions.
That was wonderful, quite inspiring. There's another dimension to astronomy that I don't think you mentioned much, and I just wondered whether you would want to comment on how that is advancing and what are the technical problems in that area. I refer to what I think is one of the great scientific revolutions of our civilization, of our scientific civilization in the 19th century, and that is spectroscopy, often neglected. There's a lot of information that's not in those pictures you showed, but is in the spectroscopic data that presumably goes with it. Could you comment on that?
Yes, yes. Well, since the theme of the talk was mostly this visual, well, the idea was to get towards this particle visualization system. I did not tackle this issue, but Gaia, in fact, has three spectrographers on board, 2 low-resolution spectrographers and 1 higher for radial velocities. This is something that is being taken very seriously, and several big observatories on Earth are dedicating significant amounts of time to spectroscopic surveys.
Perhaps you could just define what spectroscopy is for this audience.
Okay, okay. Well, spectroscopy is decomposing light in its different wavelengths. As Pedro showed you before, you have wavelengths from the X-rays to the radio. You have the visible, the infrared. It's the rainbow of the light. It's kind of a rainbow is a spectrum of a star, of the light. So you actually see the different wavelengths, and each of these wavelengths will provide different information on physical objects, because different physical processes give origin to emission or absorption in different regions of the spectrum. So this is a very important source of information, because you can, for instance, see the composition of stars by looking at a spectrum of the star. You can see that in a certain wavelength you might see that you have you can see that on the sun easily. You have absorption by hydrogen, but even other substances and molecules. You can see the composition of the universe.
And since we are talking about spectroscopy, Pedro, that little appliance that your project has developed to make a big citizen science project, could you talk a little bit about that, please?
Sure. I can, of course, comment on that. I absolutely agree. Spectroscopy is an essential part of astronomy nowadays. And like Andrea was saying, nowadays, most of the telescopes, when we build them, the first instruments that we have in our minds is the spectrographs, because they are essential, and we understand the composition of the stars, how stars form based on spectroscopy, definitely. And some of the techniques that we use in astronomy, especially to find exoplanets, we have been trying to take more on the citizen science approach. And we develop a small add-on to a smartphone, in this case an iPhone, that you can pretty much see through a spectroscopy what's the composition of the atmosphere above your head on that particular moment, and based on the quantity of particles that they are in the atmosphere and the scattered light, we can see that scattered through a spectrum, through a spectrograph, and then we measure that through the iPhone. So pretty much is a small hand-on spectrograph, and it's called iSpecs. I can provide more information. And it's a citizen science project, because then we can have the citizens, everyone with a smartphone, to measure air quality, because the number of particles in the atmosphere at that particular moment can give us an indication of what's the pollution levels of that particular location. And through a citizen science campaign, we can measure the air quality of a certain point. And we did that in the Netherlands 1 year ago. And this September, we are running a project at many European cities as part of the international flight. So I'll be happy to provide more information on that. Thank you, NF4.
So more questions, please.
I have this working? Yes. I have a basic question about our galaxy and our position within our galaxy. And when Pedro was showing the photo, it reminded me of a question I had before. It's, if we are inside, how do we know exactly that it's a spiral galaxy and our position? Most certainly in an indirect way. But what kind of information did we need to have this photo of them?
That's a very, very good question, and it's a very hard to answer. And I agree that when we moved from a heliocentric world to a more when we moved to a heliocentric world, when Copernicus really found that we were just a planet around a star, I think that was a huge jump in terms of our perspective of the universe. And I agree with you, when we figure out that we are just a solar system, a stellar system in the outskirts of a galaxy, that was another jump in terms of perspective that we have about ourselves. And usually we overlook that one. So I think the understanding of our position in the galaxy is essential. And actually it's a discovery that is less than 100 years old. was done by Jan Oort in the Netherlands as well. And I guess it's projects like Hipparcos and Gaia that give us also that location. Because if you can measure the distance to the different stars, then we can map out where we are, right? We can just put in perspective all the stars, and then we know what's the right location according to the other stars. And we see the density, and we understand, looking at other galaxies, how our galaxies should look based on these models. But I'm sure that André can provide a more meaningful.
I just want to add something. It's basically this. We need the distances with using whatever method we can use. And parallaxes in the past were not practical, so people just assumed different things. Like, for instance, people started by assuming that all stars had the same brightness, and the difference in brightness, in apparent brightness, was only due to the distance, because if you see a light further away, it will look dimmer. This was, of course, wrong, and there are other factors, but people always try to use their imagination to find all sorts of ways to find distances so they could build these maps and find our location in the galaxy. There is one tell sign that lets you, that after you've seen many galaxies, that would say, okay, I think I live in a spiral galaxy, because when you look at the Milky Way, it's a disk, and all these galaxies are spirals. And so this would be a telling sign. But this is something that we know now. People did not know. And still, it would be still a guess, because it could be the weirdest galaxy of all, which is a disk and has no spiral arms. There are a few, there is a class of galaxies that was thought not to have spiral arms and were disks. They are called lenticular galaxies. But then it turns out that seeing well in the infrared, they have very dim spiral arms too.
So we know the form of our galaxy from looking at the Milky Way. If we lose sight of the Milky Way, it's really dramatic.
But just one thing. Everything you see with the naked eye is in the Milky Way except the two Magellanic Clouds, if you've been in the southern hemisphere. And sometimes someone with a good eye can see Andromeda, M31. Everything else, every star is in the Milky Way.
Questions, please? Everybody is hungry, I suppose. Do you have time for... Okay, it's finishing on time. This is perfectly... Only possible... Sorry? Sorry. This is only possible with astronomy, clearly, that we keep the time in this precise fashion. So, we finish here for this morning. Let me remind you that we reconvene in the afternoon at 3 o'clock p.m. With a panel about light and technology. Light and technology is, of course, another of the big topics of the International Year of Light. And you will hear about the power of light, harnessing it, and also the technology, how we use light to basically to everything, from health to satellites, from bridges, telecommunications, everything. So have a nice lunch and come back at 3 o'clock. We have a cafeteria downstairs, so you can go or choose other options around.